Okay, hopefully we're streaming now. I guess YouTube takes a little while. Okay, we're up. Okay, let's get started. All right, so before I get started, let's actually just sort of clear my screen. Okay. Okay, I guess we're streaming now. Are we? Double check. Okay, say hi if you're on. Okay. All right, so I'm going to get started. And so today's topic is rustBoot. So rustBoot is essentially a project that I've been working on, and a bunch of people have contributed to this project. It's, as the name suggests, it's a secure bootloader that's entirely written in Rust. Now, the thinking over here was that this this particular piece of or this bootloader will be an effective drop-in replacement for something like U-boot. Of course, without all the bells and whistles that U-boot has to offer, but where rustBoot, if the focus is things like safety and security, then rustBoot should be the choice. So I'll talk more about the design goals. So I've actually come a little prepared for this particular stream. So here's what I'll be covering today. rustBoot, it's an intro, specifically the design goals behind it. Then we'll do a quick walkthrough of the repository itself. It's an open source project, obviously. So what's the layout of the project? We'll just quickly walk through that. And then we've also been putting together some user level documentation. So we have a user guide in the form of a book. And that's also available, again, for free online. And then we'll also do a quick demo of one of the cortex-m MCUs, specifically the NRF 52840, which I happen to have over here. I hope this is visible. I'm sorry. Yeah, this one. I think I should just pull this out. Okay. Yeah. So just to repeat that, this one. Okay. All right. So that's the agenda. Now let me get started. So the first thing that we're going to do is let's walk through the design goals. So the repo is over here, which is rustBoot. And it's an open source project, so I wouldn't say it's well documented. I'd say it's fairly well documented. We've got support. We've got a bit of a README over here. We talk about rustBoot, the fundamental idea behind it. It's a bare metal bootloader. The idea is to basically boot any kind of bare metal firmware, or you can boot into Linux itself. So that's what was one of the key requirements, because Linux is one of those things that, more often than not, we'd end up in a position where, can this thing boot Linux is a question. So in many production, or you would say many production grade bootloaders, this is an actual requirement. If you can't boot Linux, then you're sort of handicapping yourself. So rustBoot's goal is also to boot into Linux, and we have some examples of that. Of course, today we're not going to go through those examples. We're specifically going to focus on the bare metal firmware booting capabilities of rustBoot. All right, and then why rustBoot? So in a nutshell, if we want to talk about why rustBoot, you can say that These are the reasons why. So rustBoot, the idea primarily is to offer an OS and a micro architecture agnostic secure bootloader. And I'll tell you what I mean by micro architecture agnostic. How can a bootloader be micro architecture agnostic is a question. There's no magic over there. We're basically going to actually build out usable solutions and make them easily available to anybody who wants to just get started, not spend a lot of time on putting things together, packaging it correctly, getting the right kind of tooling in place, etc. Avoiding all of that, sort of making this an easy solution to sort of boot into any kind of bare metal firmware that you need. So the core goal is rustBoot's architecture is designed around a core idea. The idea is that unlike U-boot, and we'll look at some of the things that some of the things that are not desirable when you're working with things like U-boot. We'll talk about those things, but specifically on rustBoot, we are focusing on securing the absolute bare minimum and offloading the rest to systems that are actually better suited for the job. What we mean by that is the bootloader is going to be tiny as hell, all right? In fact, our target for MCUs is less than 32 kilobytes. And even in some cases, that's still big. Because if you talk about really resource constrained places, we'd still need something like 8 kilobytes. We're working on that. But for now, the core bootloader, that's basically, the full bootloader with all of the functionality that's available today, we're targeting something less than 32 kilobytes. So it has a very tiny trusted computing base. In other words, on the bare metal systems, there's no such thing like a networking stack, a file system, command shells, and all of that, which you normally have, you normally see in the de facto standard, let's say U-boot. So that's not there. The focus is to be as small as possible and, sort of reduce your attack surface. That's why we have a very small core. And then the other piece is one of the jobs of the bootloader is it doesn't have access to the operating system. So what do we do? So in that case, we basically need to come up with our own drivers and hardware configuration routines, etc. So you'll need at least a minimal hardware abstraction layer, and that's where we provide a minimal hardware abstraction layer, not just for an architecture, but for every board, because there can be a lot of differences, when it comes to the underlying hardware that's actually a part of an SoC. Things like access to flash controllers and memory. In some cases, you may have things like memory protection units, etc. So that's also something that we need to take care of. And then there's also things like access to secure hardware, obviously, because rustBoot is a secure bootloader. So if there are crypto accelerators available, crypto elements, if there's requirement for something called, in the ARM world, it's called trust zone. In the RISC-V world, we haven't yet talked about it. So rustBoot is also targeting RISC-V. It's just that we've not made those targets available yet, but we have a plan to support them. And then there's also access to serial interfaces, which is things like UART, and actually it's just UART for now. You can have other, kind of serial interfaces, but for now we're just focused on UART. And this is like the bare minimum. Like, this is all that we want to support and nothing more. All right. And the benefit of this, I will talk about that more when we get into the documentation piece. And then there's also specific support for, as I mentioned, crypto elements, which could mean that you could actually have offload any kind of crypto implementation requirements that you have, rather than in software. If you have some piece of hardware that's doing it for you, then you can simply go ahead and leverage one of the available drivers that we're building out. So both, that's when available, when the hardware is available, we're going to build a driver for it. We've got to make it available. That's because one of the goals is it has to be secure. Security is a big, requirement over here. So pretty much any secure element module, etc., that's out there and that you need support for, we've pretty much got everything in there. And then when there's no hardware available, all we're left with is, we just have to go ahead and roll our own, not roll our own crypto, but implement, have an implementation that will take care of regular proven cryptographic algorithms like ECC crypto, signature verification, or things like AES for encryption, etc. So all of that's also something that we're supporting. And then lastly, the biggest piece over here is how does the bootloader actually do secure bootloading and updating without a networking stack? I'll dive a little more into this, but in other words, it's very simply the boot update approach is what we use. We have two partitions. One is called the boot partition. The other one's called the update partition. And in both cases, we basically go ahead and say that, we have your firmware in the boot partition, which is always the active partition. We have an update partition where any update is downloaded and installed. And then when you actually need to sort of update, we do some swapping, which I will go into a little more. But that's, why rustBoot. So let me just take a pause and see if, oh yeah, somebody's joined. Hi. Hi there. Okay. So I hope that makes a lot of sense right now. So that's pretty much why rustBoot actually exists, or why I've been working on this project for a while now. Of course, not put in a lot of time, but yeah, we've been working on this with this idea in mind, right? And then there's also these features that are currently supported that we've already rolled out. We have support for cortex-m architectures. As I mentioned, that partitioning system that we have, which is flash memory, gets to be partitioned into multiple partitions, which is you have like the bootloader partition, you have a boot partition, and then you have an update partition. All of these partitions are available. And this allows us to implement the boot and update approach, which I've just sort of talked about. I'll talk more about that. And then we're also supporting the ARM, the Cortex-A chips, specifically the 64-bit ARM chips, primarily to support Linux. And then ECC cryptography for integrity and authenticity verification, the hardware abstraction layer. There's also rollback protection that we've built in. It's basically through version numbering, which I will go through more when I talk about rustBoot's, the simplest packaging that we have is we just add a header to every image that makes it a rustBoot image, which I will sort of talk about. And then we have a full memory safe core bootloader. I will dive a little more into this because this is actually pretty important to us. And also the next point, which is power interruptible firmware updates. One of the key things about rustBoot is if you actually have, while you're performing an update, if there is any kind of power loss, you don't end up with a bricked device. There's always the assurance of a fallback. And that's partly why we do the entire swapping piece. All right, and then the whole, the entire thing also comes with some batteries included, which is we've got the signing utilities also built in, so you don't have to use extra tools to sign your firmware, etc. That method's also built in. All right, so yes, that's that's what I want to cover over here. And yes, now we also have a link to the book, which is available for free. I've actually opened it up over here, so let me just quickly jump. By the way, this is licensed MIT. So please feel free to contribute to this project. Yes, I'll be more than happy to sort of, accept any pull requests. All right, then this is the book for rustBoot. So we've got, I wouldn't say like awesome documentation. We've got some fairly decent documentation, right? So we've an introduction, the goals, the features, and pretty much everything that you need to get started, at least to sort of get an idea, that's available here. You'll pretty much know what's in there. Okay, so yeah, this is the documentation. And as I said, what are the goals? The first piece that I wanted to talk about was a little more in depth about this whole why rustBoot piece. I mentioned a couple of things like, you know, we want to keep the trusted computing base small. We want a small hardware abstraction layer and all of that. Now, let's dive a little deeper into that portion as to, you know, why that's important. So here's why that's important. Today, when we look at the options available, we have something like U-boot, which is like the de facto standard. If you want to deploy a product, you know, if you want to put something in production, you're pretty much going to be using U-boot because it's well supported by many vendors. It comes out of the box in many cases. It's been around for a while now, and it's actually very great to use. But here's the problem. When you actually think about U-boot and when you try to look at its, the entire project as such, when you try to look at the entire code base, you see that U-boot's actually sort of resembling a mini operating system in itself. I mean, you can definitely sort of distill it down and say, okay, I just want the bare minimum. That is possible. Nothing's stopping us. But that's not usually how products are deployed when we actually, you know, use U-boot. But let me quickly check if there are any questions over here. Okay, right, just checking. Okay, so I was just saying that, yes. Yeah, so U-boot, when you actually think about its code base, there's so many pieces to it. You have a complete networking stack. You can go ahead and do, you know, TFTP, you can do DHCP, you can do network file storage, you can do ICMP. It's got a full-fledged networking stack built into it. It's got a whole collection of device drivers and device tree blobs. Of course, they're all per board and stuff, but still, you know, when you actually look at the number of device drivers that it supports, which means the bootloader needing access to various parts of your hardware, there's a lot. And then there's also things like integrated debug and command shells. You will have a console. For example, you'll have something like a, you know, basically that's one of the biggest things about U-boot because it makes it very highly configurable. You can go ahead and boot whatever you want once you get into that console mode. And that also apparently is one of the biggest attack vectors. That's kind of what I'm showcasing over here. Depth charge is an actual tool that's built by a bunch of people who are, it's an actual hacking toolkit for researchers and tinkerers. And one of the things that they actually look for when they use the tool is they're actually looking for this console. You know, how quickly can they gain access to a console? How well protected is it, depending on, you know, the implementation, etc. So that's another thing. And then you have, you know, support for every possible file system that you can think of in U-boot, right? So all of this stuff, it's all good. I mean, it's not bad, but it's good. But when you come to think about it, for a bootloader, this may not necessarily be required, right? And that's where rustBoot takes a different approach. Says, we don't need any of this. We simply need the bare minimum, right? That's one. And then memory safety. The other piece about this is when you have such a large code base, obviously that's a large attack surface. And coupled with the fact that U-boot is written in C, and there's, you know, if you actually look at a quick analysis of the last few CVEs, the majority of them fall into the memory safety category, right? A large number of publicly known vulnerabilities that are available. You can actually look at them. Most of them are pretty much just memory safety vulnerabilities. In rustBoot, that's not the case because it's a large part. I mean, the most important parts are actually written in Rust, the safe fragment of Rust. So there's very little unsafe code in rustBoot, except when you're actually dealing with direct hardware. I'll talk more about that as well. And then there's complexity and boot time. Obviously, U-boot has gotten a bit complex because there's quite a few things going on, and you really have to know what you're doing to work with U-boot effectively. And because rustBoot is going to keep it simple and it's going to be the bare minimum, that is actually taken away quite a bit. Additionally, you don't have support. I mean, because we're working on supporting a bootloader for bare metal systems, the idea is also to keep out things like redundant hierarchical digital signature verification schemes, etc. That's not something that actually makes sense in many cases. Yeah, and also when you're doing a lot of parsing, because when you're actually booting, you're actually doing a lot of parsing. You're pulling a file in from here and from there, you're trying to read it, you're trying to see what's in that file. Basis that, you're trying to take some action. You know, trying to reduce that is also one of the goals. And yeah, vendor dependencies. To a large extent, we are trying to use standards-based solutions. I'll dive a little more into that. Yeah. And this is the other part, what I meant by standards-based, goals that we have based on, a particular set of standards. So we've looked at the standard called IETF. It's the software update for the Internet of Things. And that's primarily what we're going with, because it's very close to what we think, makes a lot of sense in the IoT world. Primarily things like reducing your trusted computing base, ensuring that you have a minimal hardware abstraction layer. All of those things are actually part of the standard. So sort of trying to stick to that. So reliable updates. Reliable updates is a scenario where what we're actually doing over here is we are, as I said, maybe I'll actually talk about this towards the later part, because I have some pictures maybe that I can show you them, so that'll make more sense. Yeah, the other piece is predictability over performance. There's no concepts in rustBoot, things like macros and metaprogramming and async and all of that, because you want to keep it simple. You want to keep it extremely predictable, and that should be maintained throughout. And async can get quite complicated, or not quite complicated, but it depends on what you're doing, and it's not effectively simple. All right, at least I can say that. Then within rustBoot, there is no place for a heap. There is no heap at all. Everything's stack allocated, so there's zero dynamic memory allocation. That's a core part. So you don't run into things like out of memory exceptions, etc. That's not going to happen. Additionally, memory safety and type safety. This is a big thing because the entire bootloader is written in Rust, and we are leveraging all of the coolness of Rust, all of the type, the powerfulness of its type system, the built-in ownership and borrowing concepts that make Rust so good. All of that's used. We put it to use in multiple places. One of them is like something that's very much encouraged in the embedded Rust community, or actually considered a good design, which is making, encoding different states of your system into types, and then using them to ensure that at compile time, you don't end up with invalid states right at compile time. I'll just talk about that a little more if that's confusing. Okay, so that's pretty much, the goals of rustBoot and where we're heading with this and what we're trying to do, etc. Right? Let me quickly check the chat to see if there are any questions. I guess not. Okay. All right, so let me go forward. Then we have, let's talk about, what was the other thing in my thing? Yeah, the repo. Let's take a look at the repo to see, what the repo like, what's the layout, what is the structure of this repo. So we have rustBoot over here. rustBoot has boards. So there's a boards folder. There's something called the RB signer, rustBoot signer. Then there's the rustBoot folder. Then there's xtask. So the way this thing is actually laid out, I think I may have some documentation on it, but let me just double check. Yeah. Okay. I don't think I've laid it out. That's a good point. Maybe I should add it. So let me go back. Right. So we have, it's very simple. We just have like 4 main folders, which is the boards folder. The boards folder actually contains a bunch of different things. It contains the hardware abstraction layer for, your different kinds of architectures and different kinds of boards. That's the hardware abstraction layer. That's called the HAL. Then you've got the actual bootloader implementation, which means this is the bootloader. That's when you actually compile your, when you actually compile rustBoot for a particular target, say the NRF52840 board, then, you get a binary. That binary is basically this particular crate, right? It's just this crate. So this is the actual bootloader implementation, the full implementation. All right. Then firmware. Firmware is another scenario where this is basically, we've also provided a folder to sort of include test firmware. For example, for the same NRF52840 board, we also want to make sure that, you can actually test your firmware. So we've sort of used blinky firmware right now because it's just simple. You can get some blinking LEDs. I will show a demonstration towards the end, but you can do that. So that's available. So so firmware exclusively is basically saying that, whatever firmware you have, you can just drop it over there. And when we actually do the build sign flash step, then we pick up the firmware from here. But if you want to use this firmware to test, you can test. If you want to use your own firmware to test, you can actually do that. But the firmware folder is only for, firmware. And then the hardware abstraction layer. This is where, a lot of the hardware specific stuff that where I talked about, microarchitecture agnostic and board agnostic. A lot of the stuff actually sits here, right? For example, I was, in the HAL, I just jump into the HAL, I look at its source and I say, okay, what sort of hardware abstraction layers do you have for, let's say, the NRF board? Everything's right here. You can just click it and you'd be able to find that we have a flash driver. That's primarily the thing that we're offering for the NRF board, right? So that's already available for us. Okay, now then that's the hardware abstraction layer. And then sign images is not exactly currently used. We still have it over there, but it's actually, a lot of the stuff is moved into the signed images, the rustBoot signer space. So yeah. And then the update folder. In the update folder, what we have is what we call the logic that allows rustBoot to perform an update, right? All of this is pretty much the common piece of code that you'd find, or the common modules that you'd find for the rest of the MCUs. So all of them use the same update logic. So that's why it's been segregated into its own space, right? Of course, the cortex-m chips don't use this method of swapping the contents of flash partitions. They don't rely on that. They have many Cortex-A chips have their own methods. So that's a little different, except in the MCU case, we can actually go ahead and leverage rustBoot's update mechanism. All right. So yeah, in this in the update space, we just have the most important piece of logic, which is to be able to update our firmware. And I'll show you some pictures of it so that it's a little more easier to sort of mentally visualize this. But yeah, that's the entire repository for boards. So boards contains all of the hardware related pieces of rustBoot, right? That's the repo. Then RB signer is very straightforward. It's basically the signing utilities that you need to sign your firmware images. So the way you actually, when we talk about digital signature verification or signed images, verification of signed images, what we're basically saying is you will need to sign your whatever firmware you have using some private key. And then once you've signed that firmware, you can, sort of load it onto a certain partition, a predefined partition, and in Flash. And then, then we can go ahead and boot into it after verifying the signed image. I'll sort of explain how that works, but all of the utilities relating to signing are over here. So we've got a specific module for MCUs. We have different images, as I said, for microcontroller images, and then a different image format for something that needs to boot Linux, which is we're using the FIT image. Now, FIT is a U-boot standard. U-boot actually came out with the FIT format. Since there's wide support for it, why not just support that and not invent a new one, right? That's the goal anyway. So yeah, and then we also have the X task for folks who do not know about Rust quite a bit. This particular folder is your, it helps you actually do cross-compiling. So all of this stuff that I talked about, MCUs run on a different architecture. They have this cortex-m architecture, which is a different machine altogether. You want to compile that code on your host machine and then have to flash it on to some other device. There's a whole bunch of steps involved. You need to sort of compile it, link it properly, and then you need to program your board, which I'm going to show you. And in between, you need to do some signing. All of those steps, rather than do them manually, we sort of automated that, and the Xtask folder takes care of that, right? Okay, so I hope that makes sense. Let me quickly check to see if there are any questions. Okay, guess not. That's fine. Right, so now let's take a look at sorry, I think I missed something. Oh yeah, I was looking at the folder. I was looking at the layout of the repo. Then we have, that's pretty much the whole of the rustBoot repo. There's nothing else to it. It's pretty straightforward, and that's exactly what we were aiming for. Keep it simple, keep it extremely, take out as much complexity as you can, but still provide usable, workable solutions right out of the box. That's the goal, right? And I think we sort of, in a space where we've achieved it. So that's good. So that's a quick walkthrough of the repo. Then we sort of went through the book a little bit, but we'll now dive a little more. But before diving into the book a little more, let me actually mix the book and some of the code that is written. Okay, so when you actually go ahead and sort of clone this repo, clone the rustBoot repo, you'll find exactly what you saw on GitHub. So let's actually sort of dive a little into this, because I wanted to keep this a little small. Sorry, I wanted to keep this talk short and not sort of jump into this quite a bit. So keeping that in mind, I'm just going to focus on let's say you want to use rustBoot to sort of boot one particular MCU. And I'm taking the example of the NRF 52840 for today, just so that, you know, we can set some context. Okay, if I want to do that, what do I like? How do I go about doing that? One is obviously we've got some documentation over here. So if you just go in here and you go to usage, you'll see that there's a particular section for NRF 52840. It's fairly well documented, I would say, but you know, we can do better. But yeah, it's got enough information to get you started at least. So step one of whenever we talk about building, signing and flashing, because by the way, rustBoot does not, by design, does not allow unsigned images. That means any image that you are going to actually use rustBoot to load needs to be signed. And it needs to be signed using rustBoot's, signing utility, because rustBoot has a specific header format that needs to be tacked on to every image. Right. So given that's the case, let's actually click on build and flash so that I can walk you through the steps. So the first step is obviously if you want to use rustBoot directly, there are, basically speaking, there's these 4 steps, right? Yeah, these 4 steps. Firstly, when we are talking specifically about MCUs, we have to figure out partitioning, right? We have to partition the available non-volatile storage on an MCU, which is flash usually. There's some flash memory available, you need to partition it properly. In other words, you need to say, where does your bootloader go? Where does your boot firmware go? Where does your update firmware go? Yeah, those are the 3 partitions that you need to clearly upfront, provide, so that rustBoot can take up, use that to do the secure booting and update. So let's look at the partitions. What do they look like, right? So here's what it would look like when you actually think about, mentally, if you want to visualize what does rustBoot's partition look like. You got the bootloader that sits in its own partition, usually starts at 0, address 0. If you were looking at the memory map, this starts at 0. So that's where your rustBoot partition sits. And then your boot firmware follows, and then your update partition follows. Of course, this is not exactly, you could say that according to the partition, yes, it's consecutive. That means one follows the other. Lastly, we also have the swap partition. The swap partition, I'll get to it, but you can think of the swap partition as the largest sector that you can swap, or rather the smallest sector that you can actually swap. And I'll tell you why that's important in a bit. But yeah, that's how you first partition. Once you're done with the partition, then where was I? Yeah, sorry. Once you're done with the partition, you can go ahead and sorry, I keep jumping around. Once you're done with the partitioning, then you can go ahead and effectively go ahead and build the project. And taking the NRF 52840 example, let's see how that works. So I do my partitioning. I just say, okay, there's a specific constants module that we have, which I will show you. So if you actually go into source under the rustBoot project, you will find that, oh, I didn't mention this. Actually, I mentioned boards, RB signer, and I talked about Xtask, but I did not talk about the rustBoot folder. The rustBoot folder contains the core bootloader logic. It's very simple. It contains the crypto implementations that you need. That's the software implementations. It contains things like for cortex-A systems, there are requirements like a device tree and a file system. At a bare minimum, you need a FAT32 support. So all of that is available. For MCUs, you have things like, basically your partitions, what images go into those partitions, etc. All of that, is sort of contained within the rustBoot folder, which is this folder. Okay, so I was going to say, you will have a constants module over here, and we have a basic, this is basically constants as the name suggests. It's all your partitions are clearly called out. So what we're trying to say is, for the NRF52840, according to the board specs, it says that the sector size, each sector is about, hex 1000, which I presume is not entirely sure, but let me try this. Yeah, it's about 4 kilobytes, right? So that's the size, that's each page is about 4 kilobytes. So good. And then I'm saying that I want a partition size of at least 28,000 hex. And then my boot partition starts at, 2F000, and my update partition starts at this. And then my swap partition starts at this. So if I do it this way, then if you go back, you'd see that if I just was to click on partitions here, and yeah, if I was to just go back here, you'd see that, the boot partition is starting here, which means this address over here is 2F00, and the update partition is 58000, which means it's actually starting a little away. And then you've got the swap partition, which is what I am also providing as 57,000. So in my case, in the NRF52840 case, I actually put the swap partition in between. So that's possible. That's okay. All you have to do is you have to provide predetermined addresses for each partition. That's the important thing. Okay, just give me a minute. I think I'm low on battery, so let me just charge my camera up, which happens to be my phone. Just a minute. Okay, now that's done. All right, so that's the swap partition. So that's how you sort of do the partitioning. So it's very simple. You just go ahead and add some constants, or if you want to, you want to use the same board but you want to partition it differently, absolutely, you can go ahead and do it. All right, so now once that is done, then you need to sort of go to the next step, which is compiling, signing, and programming. So all of this is actually explained a little bit over here, so that it's not too alien as such. Yeah, it's all should be self-explanatory. If it's not, please do feel free to raise a sort of an issue on GitHub. For the book, we have a separate repo. You can go ahead and raise one. We'd be more than happy to sort of take feedback and change that. All right. Then the compiling, signing, and programming, we sort of said, this, rather than sort of do these individual steps, at least the manual or this book will help you get everything done in one go to effectively get started. So you can do that. By the way, all of this, the compiling and the signing specifically, the keys that we're using are all test keys. Okay, we have made the private key public, so it's useless. The entire signing mechanism is useless. Just so that for people who don't know, how crypto works, you cannot reveal your private key. If you've revealed it, it's done. It's as good as being compromised. It's just pointless. But for the purpose of this case, we've actually used a private key we don't care about, which is being used for testing. All right, just keep that in mind. So the key is over here. It's called the ECC256DER. That's available in our folder. You can actually go ahead. We actually use that key for testing all of these. That means for all the CI work, we use the same key. All right. So in the compiling, signing, and programming phase, that's exactly what we do. Once you've got the partitioning set up for your board, and you have gone ahead and said, okay, this is my boot firmware, that's my update firmware, and you've got the bootloader ready, you can go ahead and actually build your project now. And I'm going to do that. I'm going to demonstrate that in some time. But that's kind of what you need to do when you want to actually at least test rustBoot, right? So and that's what this is entirely detailing. All you need is when you actually compile with this command that I'm going to show you, you're going to compile all three pieces: the bootloader, the boot firmware, and the update firmware. And then all three pieces are going to be flashed according to the partitioning, according to the partitioning scheme that you've chosen into the relevant slots. And then for this use case, at least, we have Blinky firmware in both the boot partition and the update partition. So in the boot partition, we have Blinky firmware that blinks the green LED. In the update partition, we'll have firmware that blinks the red LED. So the goal is very simple. You boot into the boot firmware, you blink green for some time, and then you actually do the update. And then you do the swap actually of the firmware. And then you go ahead and you go ahead and start using the updated firmware, which now starts blinking red. So what you will actually see when I demonstrate is, you will first see that once I compile and sign and program the board, the green LED starts blinking for a little bit. Then the LED stops. And then the same LED after a while starts blinking red, which basically means that the update has taken place. So both secure boot and update have taken place. I'm sorry, both firmwares have also been signed in the process. That means they've also been verified. Right? I sort of hope that makes sense. You need some prerequisite tools, etc., to install them. So this guide should be fairly simple to follow. Oh, I think there's a... Oh, okay, I need to change this. So you also need to provide version numbers of your firmware. That's how I remember I mentioned we provide rollback protection. That's because we have version numbers also included in the signing process. The actual command is something like this. You can look at this, this is the actual command that you need to provide. When you do that, you should be able to go ahead and actually build, sign, and program any cortex-m MCU once you've done the partitioning correctly. Okay. Yeah, I know that this may not seem very straightforward, at least when I'm talking, but I think when you actually read the book, it should be pretty straightforward. Okay. Let me see if there are any questions. Okay. All right. Looks like there's another question, but it's sort of... Okay, I don't think I can understand that, but fine. Let's just move on. Yeah, so that's pretty much it. And we've also mentioned that, how do you actually check whether everything is working and it does what it says in the box, right? So what I just discussed, which is blinking the LEDs, is what we use as a mechanism to figure out whether this rustBoot is actually working correctly. Okay. All right. Now, before I jump in, I also want to spend some time talking about one very important thing. What is this? What is this thing that I kept talking about, MCU images? When I say I signed some piece of firmware, what does that actually mean with respect to at least rustBoot? It means nothing but I am going to construct a header, which is 256 bytes of a header. And then I'm going to just prepend that header to the actual binary of the boot and update firmware. So those are the pieces of firmware that we want to verify. So I'm going to create or construct a 256 byte header called the rustBoot header. And I'm going to prepend that to our image. That header actually contains the signature, and it also contains a whole bunch of things. It's a very, very simple header format. You can call this a container as well, but it's the most simplest thing. And that's exactly what we wanted to do. Keep it simple so that you don't have unnecessary, you can actually have very elaborate, complicated, container formats. When we do that, the parsing logic and the requirements on parsing go up really high, and you can end up making a lot of mistakes and stuff. And that's not the case with rustBoot. Okay, so the header is very simple. It looks like this. you can fit that entire thing. So it's got something called a magic value. You can, rather than going through all of these fields, you can just know that every field in the header is a type length value. It's as simple as that. So you take the 256 byte header, you create it, you just tack it onto a, just prepend it to a firmware image, and then you have your rustBoot image. That's it, right? That's about it. And then this is what, whenever rustBoot tries to authenticate or verify a signed image, it's going to look at the header. It's going to look for, a bunch of different things first. And then it's also going to look at the signature, which is over here. It looks at the signature. It tries to verify the signature using a, it depends on the hardware, but using a public key that is actually stored in the either embedded inside the bootloader or is sort of fused into some on-chip one-time programmable fuse or something like that into the hardware. Both, like everything, all options are supported, but the basic idea of signature verification is this when it comes to rustBoot, right? And so the entire thing about what the header is, how many bytes do we need, etc., all of that is sort of covered over here to give you a basic idea. And that logic, if you want to sort of take a look at that, that's what is present in the core bootloader. You can go look at the parser module, which is pretty self-explanatory. We sort of talk about exactly what we saw: the version number, the timestamp, the image, all of that is present in there. All right. Then image is the image. This particular module, let me also speak about this because we're going to be talking about it. This particular module is one module where you want to keep in mind that the core logic of the entire partitioning scheme that we're doing, the crypto pieces that we're using, all of that is sort of glued together in the core bootloader using this particular module, which is image.rs. It sort of describes the, what a valid rustBoot image looks like, what possible states can it exist in when you're actually doing an update or when you're checking its validity, etc. All of that is in this particular module. Of course, and okay, without confusing the folks who may not know what Rust is yet, sealed traits is nothing but a pattern. You can limit the number of possible states and partitions that you can have. So we sort of use the same pattern in Rust to ensure that you can't just create your own states and your own partitions just like that. Sort of lock it down, right? All right. So that's in a nutshell. That's the simplest thing that when we talk about rustBoot as it relates to MCU. MCU firmware, MCU booting, secure updates, etc. The idea over here is that, and you may be wondering, okay, how are you doing the update when there's no networking stack? The goal is this: networking is actually offloaded to the bare metal firmware or whatever is actually running. The job of actually downloading and installing the update firmware is not that of the bootloader, it's that of the firmware that you load, right? Because we've already verified that you can go ahead and download some piece of code and have it installed in the right partition. When you reboot, that's when rustBoot gets to check whether or not there's an update available. If there's an update available, let me validate it and see if it works. If it works, great. I go ahead and do the update swapping, and then I start using the update partition. Okay. Yeah, that's it. That's in a nutshell how sort of, actually not a nutshell, a high level overview of how rustBoot works, how it's laid out, how what the repo looks like, what the book is for, and how much information it can provide to you. And now the last piece that I actually wanted to talk about today wanted to show you a demo. Of course, all of the different boards that we already support, they're all working. You can check each one of them out if you have a different board. But since I have my, let me just see if I can show you guys this again. Yeah, this board right now is blinking red because it's already done the update. It's already, sort of working. I'll show you when you actually, do the flashing. It should blink green first, then pause for a little while, and then start blinking red. Okay, so I'll show you all of that now. Now, in order to do that, all I need to do is, just go in here and flash my board. So the way I'm going to flash my board is, since I've already done this, I'm going to sort of just do this. All of this is like dummy, there's a dummy version numbers, dummy keys, all of that. Just calling that out again. If somebody just assumes that you can just use this, no, you cannot, because this is just test. Just to so that, our CI works properly and, we have testable examples. Right? That's it. So if I was to go ahead and run this, we compile rustBoot, and rustBoot's got a whole bunch of dependencies, but then this is where Xtask is actually kicking in. You saw the Xtask project, the entire build mechanism, because there's so many things that we need to compile and then put together and then work together. Yeah, now we're doing the flashing. Now, after we flashed everything, that's the programming pages piece. Now, you should quickly see, let me just show you. You should see that it's blinking green. Yeah, I hope you saw it was blinking green for a little while. I hope you saw it. And then now it's blinking red, right? Okay, I hope you guys saw it, because otherwise I'd have to do it again. Let me double check the chat to see if you guys actually saw it. If you want me to do it again, I probably can do it. Okay, so let me just check the chat. Yeah, I guess you guys did see it. Okay, fine. Good. So in that case, if you actually think about it, this particular let me actually talk about what actually happened over here, because there's a lot of stuff that just flew through. So I sort of ran this command, and the entire build flow kicks off. We build rustBoot first, which is what we have here. Then we build the firmware. Then we go ahead and build, first we build the firmware first. Then we build rustBoot next. And then we go ahead and start, because when you build the firmware, you actually get an ELF file. You don't get the binary file. We extract the binary using some, object copy stuff. And then we go ahead and sign the binary images, only the binary images. When we do sign them, the firmware, you will get this output for each one. That is, for the boot firmware, you have this output, which says, okay, we're signing the boot firmware with this particular ECC curve. And the key, public key, as I just mentioned, is over there. By the way, so what you need to think about is this particular file is not actually a public key. It contains the private key. In ECC, if you know anything about ECC, you can derive the public key from a private key, because you just have a generator. Okay, without going into all of that, this particular key is what's going to be used to actually sign our firmware. Once we provide a version number, then we sign it. We get, and I want the output image to be called this. So all of that is done. It's done for both the boot firmware and the update firmware. And then we erase the entire chip, and we go ahead and flash the boot firmware. Second, we go ahead and flash the boot firmware. I don't know why this ProBars, which is our flasher and debugger and programmer, is throwing these debug logs. I need to check that. But anyway, then we go ahead and flash basically the rustBoot into the partition that we put together. And once that is all done, then you saw, the green LED blink first and then the red LED blink later. That's what happens, just to sort of test that, rustBoot is working. All right, so that's a quick demonstration of rustBoot. All right. Now, if there are any questions, I guess I can take them. By the way, sorry for the interruptions in between, etc. Because I actually thought this would go smoothly, but I messed up a little bit with some of the configuration and stuff. Sorry about that. But yeah. All right. So I guess there aren't any questions. So I think I can go ahead and just stop the stream. But in any case, before I go, if there are any sort of questions around it, please feel free to use the GitHub repo to reach out to us. You can use either the issues tab or the discussions tab, or you can reach out to me separately as well if you feel it's got my Twitter and my other contact info in that. So please feel free to reach out. And if you'd like to contribute to this project, there's fairly decent amount of contribution that has come up from different places. So very happy about that. I didn't expect that to actually happen. Thought this was just going to be, a side project. But since it's actually doing pretty well, we'd be more than happy to sort of add more to it. And in case there's anything that any other discussion that you'd want to say, rustBoot, why don't we actually think about this or that, or why shouldn't we support X or Y? We'd more than be happy to, sort of have those conversations. All right. With that said, thank you, and speak to you again next Friday. Have a good day. Bye-bye.